Hello and once again welcome. Today I am going to start with a topic uh, called Work Energy Theorem. And this is a topic related to physics for Ibdp course, and it's a part of a chapter called Work, Energy and Power. Work Energy Theorem, you can see on the screen, is a very important theorem which gives us a relationship between the energy, in fact the change in the energy, and the work done. It actually tells us that whenever any work is done on a body, some energy is added up to that body or some energy is taken away from that body. Okay, so there is always some change in energy taking place in a body whenever work is done on a body. The work done is connected to the energy in that way. And this theorem is a connection between work and energy. So let us start with the work energy theorem right away. Work energy theorem, if you want to understand, first you should know that there is something called kinetic energy, which is related to a moving body. And this energy is a scalar quantity and it is given by a formula half times the mass of the body times the square of its velocity. As I told you, kinetic energy is connected with a moving body, and a moving body has to have some velocity and some mass. So the kinetic energy of the body, moving body, is given by this formula, half times mass times v square. Now, the velocity may keep on changing. So suppose the initial velocity is say u, and the final velocity is say v, then the kinetic energy in this scenario will be something called initial kinetic energy and final kinetic energy. So final kinetic energy will be half times m times v square, that is final velocity square, and initial kinetic energy will be half times m times u square, which is the initial velocity square. And the change in kinetic energy will be represented by this particular equation. That is delta Ke is equal to half times mass in the bracket v square minus a u square. V is the final velocity, u is the initial velocity. So you know what is kinetic energy of a moving body of object mass. Now let us try to find out the work done by force acting on a body. And before that, let me tell you what is this work energy theorem. First of all, you should know what is work energy theorem. Work energy theorem states that the work done by all the forces acting on a body, I repeat, all the forces. Okay, so you are not going to leave a single force. So any body can be acted upon by either one force or two force or three or four or many more. So these forces can be internal forces, this can be external forces, this can be forces which are of certain type, this can be forces which are of some other type. So whatever the type, whatever the the nature of that force, you have to consider all the forces, right? So work energy theorem states that the work done by all the forces acting on a body at that particular time is equivalent to, or is equal to rather, change in the kinetic energy of that body. This is your work energy theorem. Once again, I am repeating. The work done by not one or two forces, by all the possible forces which are acting on a body at that particular time will be equal to the change in the kinetic energy of that body. Now, this particular work energy theorem is very useful, and you will come to know in a short while why it is very useful. First, let us try to understand what is the meaning of this work energy theorem. Okay. Now, consider this body Okay, this body whose mass is say m, okay, and a force is being applied to this body. A force applied is F. Okay, so this force is being applied on this body mass, which is kept on a horizontal surface, right? Okay. Now, because of force, it's a net force, okay? It's an imbalance force. So, whenever an imbalance or a net force acts on a body of mass m, then acceleration will be coming in picture. So, this body will be accelerated. When this body is accelerated, obviously there will be some change in velocity taking place. Okay, so the velocity of this body will slowly increase. Okay, and this velocity will make the body displace or move. So the velocity, let the velocity introduced into this body be v, and the displacement taking place in this body be s. So we have so many things now with us. We have a force acting on a body of mass m. Because of this force, which is a net force or an imbalance force, because of this force, there is some velocity gained by the body, and because of this velocity, the displacement is taking place, right? From say A to the point B. Displacement is in the direction of A to B. Okay. Now, let us try to find out the work done due to this single force F. Okay, right now we are considering only this single force F. Okay, so the work done due to this force F, okay, will be equal to, we know by the definition of work done, it is a scalar product of the force and the displacement. So work done due to this particular force F will be equal to F dot S. And because the direction of this force and the direction of the displacement both are same, so the angle between the two will be 0. So F dot S will be Fs cos 0, and cos 0 is nothing but 1. So ultimately the work done will be Fs with a positive sign. So you will get a positive work, some value of positive work you will get, right? Next, what is the meaning of this? Whenever a positive work is done on the body by this force F, what is happening is the velocity of this body is increasing. So positive work is associated with increase in velocity. And because the velocity is increasing, okay, the kinetic energy will also be increased. So kinetic energy is also increasing. So you can see that positive work, when it is done on a body due to some force, then it always results in a increase in the kinetic energy, right? So here we say that whenever the positive work is done, work done is positive, you are giving or you are supplying energy to the body. Okay, and when you give or supply energy to the body, the kinetic energy or whatever energy, okay, it is going to increase, right? So positive work is associated with increase in energy and increase in speed. That is understood from this demonstration. Let us move on to the next demonstration, that is demonstration number 2. Now what I am trying to do is, now I am trying to tell you that this body of mass m was already moving from this point A to the point B. Okay, it was already moving, it was already getting displaced from A to B. Okay, and suppose that now you are applying a force in this direction. Okay, you are trying to apply a force in the direction opposite to the direction of the motion of the body. So if the body was moving from A to B, you are applying the force on this body in such a way that the force is against or opposite to the moving body. Okay, what will happen now? Again, work done due to this particular force, okay, we can calculate using the same formula, scalar product of force and displacement. So work done due to this force now in the second scenario will be F dash S, which is equal to Fs cos of 180. Now why 180? Because now in this case the angle between your force and the displacement is 180. See, force is in this direction and your displacement is taking in this direction, right? And you can see the angle between them is 180 degree. So theta will be 180, so cos of 180. And cos of 180 is minus 1. So ultimately the work done will be negative Fs. So you get this as your work done, negative Fs. Here we say that the work done is negative because of the negative sign. We say that the work done is negative. Now, what does negative work done indicates? Negative work done indicates that the velocity is decreasing and the kinetic energy is also decreasing. Obviously, when a moving body is pulled, okay, in the opposite direction of the motion, if a force is applied, what is going to happen? It is as good as you are applying brakes to a moving car. So when you apply brakes to a moving car, what is going to happen? The velocity is gradually going to decrease and ultimately the velocity will become zero and the car or the vehicle is going to stop. So the velocity decreases, and when the velocity decreases, obviously the kinetic energy will also decrease. So can you say that a negative work done is associated with a decrease in the kinetic energy? Yes. So work done is negative work done is associated with a decrease in the energy, okay, and decrease in the velocity as well, right? So this is the concept, this is the essence of something called work energy theorem. So in work energy theorem, I have just taken an example of one force, okay, but actually work energy theorem states that if a body is acted upon by too many forces, okay, it can be one, it can be two, it can be many forces. So you have to calculate the work done by all the forces on that body, and that work done will always be equal to the change in the kinetic energy of that body. This is your work energy theorem. Now, I have just made you understand the meaning of work energy theorem. So far, I haven't spoke to you about the significance of this work energy theorem. So let me tell you about the significance of this work energy theorem. What is the importance of this work energy theorem? See, if you want to find out the work done due to some force, okay, work done due to some force or due to a group of forces, okay, due to a group of forces, okay, then normally you are going to use this formula F dot S, okay, but this formula is restricted to a force which should be constant. So if work done has to be found out or calculated, okay, for a body in which the force is not constant but it is variable, then you cannot use this formula. In that case, you will have to use the formula integration from x1 to x2 f dash ds. This is the formula that you are going to use if you want to find out work done, okay, due to force, due to a variable force, right? Okay, so you know that there are a couple of formulas which will help you in finding the work done due to a force. If the force is constant, you are going to use this formula. If the force is variable, you are going to use this formula. But looking at these both formulas, you will come to know that to find out the work done by a force on a body, you must have the knowledge of the force applied on that body and the displacement taking place in that body. Both the things you should know. Then only you can use this formula. But what if I say that you don't have any information about the force acting on the body and you don't have any information about the displacement taking place in that body? Still, if I want to find out the work done on that body, then how and what we are going to do to find out the work done in that case? And the answer to this question is you will have to use something called work energy theorem. So this is the essence, or this is the importance of this work energy theorem. Work energy theorem says that work done due to all the forces, okay, due to all the forces is equal to the change in the kinetic energy. The change in the kinetic energy. So, if you want to find out the work done by all the forces on a body, even if you don't know the force, even if you don't know the displacement, but still, if you have the knowledge of any kinetic energy taking place, any change in kinetic energy taking place, then we can still find out the work done, okay, by the forces on that body. So this is an alternative way of finding the work done, okay, in such cases where the force and the displacement is clearly not mentioned in the question. This is where work energy theorem comes in picture. It becomes very handy. And there are so many other things which you can calculate. You can calculate the velocity at a particular time of a body, okay, if the work done is calculated, okay, because it is related to kinetic energy, right? So half mv square. So v square, the velocity of the body at a particular instant of time, also you can find out using this particular work energy theorem, okay. So work energy theorem is very useful theorem, and later on you will come to know when you do some numericals on this work energy theorem that how useful this work energy theorem is. Now before that, before we go to numericals, let us try to prove this work energy theorem. So the proof of this work energy theorem has been given by me over here. So the proof of this work energy theorem goes this way. We know that the work done due to all forces, okay, is equal to F dot. Now let us take the example of variable force. So let us take F dot ds, okay. So this is a variable force, okay. Constant force is a kind of a variable force. So let us take the derivation of the variable force itself. So when there is a variable force acting on a body, work done will be equal to F dot ds. This is the formula, okay. Now let us take this general formula, work is equal to F dot ds, as dw, that is small work done, is equal to F, that is the force, times small ds, okay. So this happens to be a general formula for finding the work done, okay. A very small work done will be equal to F into a small displacement ds, right? Now if you want to find out the total work W will be equal to the integration of this dw. So right from here we will start integration of dw. So when we do integration of dw, it will be integration of F dot ds. When it is integration of F dot ds, it will have some limit from x1 to x2. So it will be x1 to x2 the limit F dot ds, and F can be replaced by ma because we know F is equal to mass into acceleration. So your formula reaches integration x1 to x2 ma dot ds. Till here we have reached. Now we know that acceleration is equal to dv upon dt, rate of change of velocity, okay. Acceleration is equal to dv upon dt. This dv upon dt I am going to multiply and divide by ds, okay. So multiply by ds, divide by ds, which I can always do. On doing this, now what I will do is this ds upon dt, this portion I am going to write as v, because I know ds upon dt is v. So this ds upon dt will be written as v, and what is left? Dv upon ds. So that is over here, dv upon ds, okay. So this a can be ultimately substituted by v times dv by ds. So from this stage, from here, in place of a I am going to put this. So my dw, integration of dw will be equal to integration of mass I am keeping as it is, and a I am replacing by v into dv by ds. So can you see m into v into dv by ds, and this ds was already there, this ds that was already there, right? and this ds and ds will get cut, and now my formula becomes integration of, now this was x1 to x2, right? Now you can see that once ds gets cut, now the variable has changed to dv. From ds it has got changed to dv, that is velocity. Now we are integrating with respect to velocity. So definitely our limits will also be changing from position to velocity. So from x1 to x2, we'll have to change it to v1 to v2. So v1 to v2, mv dv. This is the formula that we have reached. Next, m being constant, I will remove it out. So m will come out and I'll get m integration v1 to v2 v dv. So this is my formula now for the total work done. So my total work done W will be equal to integration of dW. And now from here what I will do is, the integration of V is V square upon 2. So I'm going to write that V square upon 2 in a rectangular bracket. M is constant, which is outside. And the limits V1 and V2 I'm going to put over here on the side of the rectangle. V1 at the bottom, V2 at the top. This is how we generally solve definite integration problems. Okay. So now your work done works out to mass bracket V square upon 2 V1 to V2. Now this 2 being constant, I'll bring it out. So it will become m upon 2. And inside the bracket, I will be left with V square going from V1 to V2. Now to remove this rectangular bracket, this m upon 2 I will keep as it is. And this V I will replace by V2. So it will become V2 square. And then minus. And the V I will replace by V1. So it will become V1 square. So V2 square minus V1 square. So our formula has reached to this stage. Fine. Next slide. W, the total work done, is equal to integration of dW equal to, now we have reached this stage. Okay. Now let me expand this and write m upon 2 into V2 square minus m upon 2 into V1 square. So can you see I have written here half m into V2 square minus half m into V1 square. Now this half m into V2 square is nothing but your kinetic energy final. Okay. And half m into V1 square is nothing but the kinetic energy initial. Okay. Because initial velocity was V1. So kinetic energy with V1 in the formula will be initial kinetic energy, right? This is equal to kinetic energy final minus kinetic energy initial. And this kinetic energy final minus kinetic energy initial is nothing but the change in kinetic energy, right? So ultimately you get on the right hand side change in kinetic energy. So starting with work done by all the forces or due to all the forces, you came to this point, that is change in kinetic energy. So this was a derivation or the proof of your work energy theorem. Now in this particular session, as I told you, I have just made you understand the theoretical aspect of this work energy theorem. Okay, you don't know how to solve numericals based on this. Okay, so in the next video I'll be coming up with so many numericals, okay, connected with this work energy theorem. For today, that's all, and I'll come back with some more videos in the future. Till then, goodbye, take care all of you.